Okay, in this lecture, we're going to apply a couple vector calculus theorems to transform the laws of electromagnetism, which are embodied in Maxwell's equations, into a differential form, meaning going from an integral formulation to a partial derivative or differential formulation. Let's start first with Gauss's law. So as you may recall, for Gauss's law, the flux, electric flux through a closed surface around some electric charge within it is related to the charge that is enclosed by that surface divided by the permittivity constant of free space, epsilon naught. So let's say I have a point charge here on the right, charge Q, and I'm integrating over the surface area of a sphere at a constant radius r around it. If I integrate the quantity E dot dA, that's the electric field, dotted with the area vector of an infinitesimal element of area dA, it points away from a closed surface. In this case, they're parallel. So that E dot dA integrated over the whole surface area of a sphere, if it were a constant, that's 4 pi r squared, has to equal the charge enclosed over the permittivity constant. Just to remind you about Gauss's law. Now, to do this, let's first start with the right side here, the electric charge that's enclosed. That's the total charge within the bound surface, but we can relate it to the volume integral of the differential electric charge density. Usually that's abbreviated by the Greek letter rho, and that refers to the electric charge per unit volume. So, for example, coulombs per meter cubed. That would be rho. So we can relate that charge density if we integrate over some volume v, rho dv. The integral of that will give me the electric charge enclosed within that volume. Now, in vector calculus, there is the divergence theorem, and that can transform surface integrals into volume integrals. Specifically, that can be applied to the electric flux. So the electric flux, usually abbreviated by the uppercase Greek letter phi, is the surface integral over a closed surface of E dot dA in the case of the electric field. Okay, so if E dot dA is that flux through this closed surface, by divergence theorem, also known as Gauss's theorem, we can relate that to the volume integral of the divergence del dot E, the divergence of the electric field E. So that's the power of the divergence theorem. Why is that powerful? Well, that means the left side of Gauss's law, the surface integral that gives me the flux, can be replaced by the volume integral of the divergence of E, and that is 1 over epsilon naught times the volume integral of the electric charge density over the same volume V. Now, what's so special about the volume I choose? Well, physics can't depend on the shape and volume that humans choose. It's a law of nature. So it should be independent of any volume you choose. So for that to be true, then it's the integrand within each integral that has to be equal. So that can only be true for all possible volumes if we have that the divergence of the electric field, del dot E, equals the electric charge density rho over epsilon naught, the permittivity constant. So there you go. There is a differential form of Gauss's law in electromagnetism. It holds for every point in space, and it's relating the divergence of E to the charge density at that point in space. We transformed an integral into a partial differential equation here, because the divergence operator, recall, has ddx, ddy, and ddz components that are dotted with the ex, ey, and ez components as shown here. Okay, that was for Gauss's law. That was one of the laws of electromagnetism for electric charge. But recall, there's also the magnetic field, and there's equivalent Gauss's law for magnetic fields, but we don't have the equivalent of magnetic charge, not magnetic charge of a single pole, like just a north pole or just a south pole, the equivalent of like a plus charge or a minus charge in electricity. There are no magnetic monopoles. We can only have magnetic fields arising from currents. And so the divergence of B is equal to 0 because the right side here was 0. So the similar transformation or similar transformation of this surface integral for the flux, for the magnetic flux in this case, tells us that the divergence of B is also 0. So there are two of the laws of Maxwell's equations, two laws of electromagnetism, which have been transformed into the differential form. But that's not all. There are more. So let's next address Faraday's law. So what is Faraday's law? Well, Faraday's law of induction tells us that if I integrate the electric field around a closed path, that's what the circle and integral sign means, over some path C, what's enclosed in there would be this time derivative of the changing magnetic flux. So basically a changing magnetic flux creates an electric field. That's how we reason or interpret this law of electromagnetism. So here's the time derivative. There is a negative sign there, and then the flux is B dot dA. We can swap the order here. We can put the derivative and bring it inside, and it's just the derivative of the magnetic field B dotted with an unit area of dA for this law. I didn't draw a picture here, but basically we have, for example, some path C that we're integrating the electric field around, and that might be containing, let's say, magnetic field lines pointing out of the page. So there's my B. And if that magnetic field is changing in strength so that dB dt is not 0, the change in time of the magnetic field is not 0, we induce an electric field here on the left side. So that's Faraday's law written that way. But we can transform the left side, that is this circulation integral, the line integral of the electric field around this path C, into a curl of the electric field E using Stokes' theorem. So I've replaced the one-dimensional circulation integral with a two-dimensional surface integral, replacing it with the curl of E in the integrand, or del cross E. So what that tells me is the integral of del cross E, the curl of E, over some surface, that's the surface that's bounded within this path C, is equal to minus the surface integral of dB dt, the change in time of the magnetic field. Now again, the laws of physics can't depend on what path C we choose and thus what surface. So for this to be true in general, we have to have that the integrands are equal, and that tells us that the curl of E equals minus the time derivative of B. So this is the differential form of Faraday's law. So we've transformed it from this integral formulation, which I've written up above, into this partial differential equation again on the bottom there, that's boxed. All right, we've got 3 of Maxwell's equations down. Really one more to go, but really that one more has kind of 2 equations within it. So let's move on to that. That is the differential form of Maxwell's and Ampere's laws, or Maxwell-Ampere's law. So, in addition to the induction of an electric field by changing magnetic field, we also have the induction of a magnetic field from changing electric fields, as well as by electric currents contained within some surface or some path. So combining these two laws, Maxwell's law of induction with Ampere's law, I have the circulation integral of B dot ds. So that's magnetic field integrated again in some path that can contain some enclosed current I. So that's my enclosed current times the permeability constant mu naught. So that's the Ampere's law part. Basically, again, if I have some path C, right, and it's containing, in this case, some enclosed current, then I get a magnetic field that's induced. So I'd have a magnetic field going around in that path. So that's the Ampere's law part. However, when Maxwell was looking at the laws of electromagnetism and noticing some symmetries, he introduced another term, and that's this term here. If you like, it's Maxwell's law of induction, where we have the flux, the electric flux passing through the surface bounded by that curve or path C, E dot dA, the time derivative of it. So if the electric flux is changing, and now I multiply by two constants, the permeability and permittivity constants, mu naught and epsilon naught. I don't have a minus sign like in the previous Faraday law of induction. That goes to a plus sign here. But that's this part. A changing electric field on the right side in time can induce a magnetic field as well, just as a current, electric current, can induce a magnetic field. Okay, so that's Maxwell's law of induction and Ampere's law. We can relate the enclosed current here on the right to the integral over the surface of the current density. So this is the current density, J. That's the J that's inside the integral there. And that's basically the amount of current divided by the area. That's if it were a constant, but at any given point within this bounded path, at any given point, the current per unit area perpendicular to the surface is the current density. Okay, so let's start rearranging things again. The left side is the magnetic field part, the circulation of B, the integral of B dot ds over the closed path C. And then I have dA dotted with, now I'll write J for the current density, because remember J dot dA is the enclosed current, so I'm integrating over a surface integral. So there's the enclosed current, J dot dA, if I integrate over that surface. But I also have the Maxwell term that was E dot dA, but there was a time derivative. I'm going to bring the time derivative inside. So I have dE dt. I have an epsilon naught I need to put in front there. And both that term and the Ampere's law term have a mu naught in front, so I'll put that outside the integral there. Well, I could put it in front of the parentheses also just as well. So I've just kind of transformed here, substituting in the current density J for the enclosed current and putting in the integral for the surface integral across that bounded path. And the left side stays the same. That's the circulation of B. Now, here we can apply Stokes' theorem. So a circulation integral like B dot ds can be written in terms of the surface integral of the curl of the field, in this case the magnetic field. So del cross B is the curl of B, integrate over the surface S, that is the surface contained by that path C for the circulation. So that's a transformation we can do. And so what that means, the left side here of this Maxwell-Ampere law is the surface integral now of the curl of B. And the right side, by using our current density and swapping the order of the time derivative, is the surface integral of dA dotted with epsilon naught dE dt, the time derivative of the electric field, plus the current density with a mu naught out front. All right, so these are two surface integrals, left and right side. For that to be true for any surface we choose, physics can't depend on the surface I choose, the integrands have to be equal. So it can only be true for all surfaces if that curl of B equals the time derivative of E multiplied by mu naught epsilon naught plus mu naught times the current density. And that forms now the differential form of Maxwell's and Ampere's laws. So as one partial differential equation, albeit complicated because it's using the curl of B in this case. So what we've done now is we've taken the laws of electromagnetism embodied in Maxwell's equations, and we've transformed them into differential equations, which will be very interesting to use. Among other things, from these equations, in the next lecture, we can find that electromagnetic waves are a result or a consequence of these laws of electromagnetism. But we'll save that for another lecture.